workshop number 2.
Sorry about that.
In a series of 4 workshops. So last week, we looked at localization and mapping, and we had both a presentation part and some hands-on experiments part. So we're going to keep the format, but we learned from, so last time was the first time we did a workshop like this. So we learned from the experience a bit, and we are going to keep things a little bit more beginner friendly this time. And then we also have open source repository with instructions for installing everything and for following the tutorials step by step. Tianyu or Arash, do you guys mind pasting in the chat the link to the GitHub repositories in case anyone has not seen it before and wants to take a look at that? Yeah, and then put this in the chat as well, so it can be easy to click. Yeah, so last time we had localization and mapping. Today we're going to talk about motion planning. And next week, we're going to have Professor Baris Axonley from STSU lead another tutorial on optimization. And then finally, we have a new one from Professor Sean Gao from the computer science department at UCSD, which will look at reinforcement learning. So today we're starting with motion planning, and I think it's 4:06 now. So Tianyu, I think you can go.
Yeah.
And yeah, sorry, last thing. If you have any questions, feel free to interrupt. That's the point of a workshop. We are trying to keep this as interactive as possible.
All right. Hi, everyone. This is a workshop on robot motion planning. My name is Tianyu Wang, and I'm working with Nikolay Atanasov in the Existential Robotics Lab at UCSD. And yeah, so all of our material are hosted on this GitHub repository. If anyone has any trouble accessing it, please let us know. Otherwise, we will find the demos that we showed today in this GitHub, as well as their instructions on how to install Python and also instructions on how to run the code on the wiki page of this repository. So if you haven't installed Python yet, please do so. And also just download this repository, as we will, as later when we show the examples, you can also run it on your computer. Okay, so maybe there are some questions about modules not found. So if you can follow the instructions, I'm not sure if it's there, but if you just do pip install matplotlib, then yeah, so with these kinds of questions, we can solve as we go through the examples as well. Yeah.
Yeah, let's start with the presentation, and we can get to these questions later when we are in the examples. And then if people have not followed the installation instructions, you can do it now before we get to the demos. But you should also listen to the presentation.
Yep. So the topic of this workshop is about robot motion planning. And for example, when we open up Google Maps, we are often using this feature. So we want to find some path from point A to point B. And oftentimes there are really multiple paths that starts from point A and ends in point B. And we usually want to find what is the fastest route or shortest route from A to B. So the way we solve this kind of problem is to consider a shortest path on a graph. And we will introduce what is a graph here. So a graph is a set of nodes. And in this example, we will have node 0 through 6 in these circles. And there are edges connecting the nodes. For example, there's an edge between node 0 and node 1. I'm not sure if you can see my cursor moving around. Do you? Okay, great. So there's an edge between node 0 and node 1. And also there's a weight associated with each edge. For example, this edge from node 0 to 1 would have weight 4, which means that the distance from either 0 to 1 is 4, or from node 1 to 0 is 4. And the problem that we are trying to solve here is some sort of shortest path problem from node, like what is the shortest path from node 0 to node 6. And with first glance, it might be hard to just come up with a solution because there are really a lot of nodes and a lot of edges. And maybe we can start by building some intuition on how we find such a solution. So we start from the initial node 0, and we just look at its edges. So it has two edges, one pointing to node 1 and another one pointing to node 2. And let's just ignore all the other edges for now, because we pretend we haven't seen the other ones. And we can ask, maybe you can ask some questions like, if I try to go from 0 to 1, can I guarantee that the distance from node 0 to 1 is just 4? Can anyone try to answer in the chat box? Yes or no, maybe. Okay, so there are people saying yes and there are people saying no. So yeah, so it could be the case that the edge from 2 to 1 is just 1, in which case we will have a shorter path from 0 to 2 first, and then to node 1, which will incur a distance of 3. So we cannot say that the distance from 0 to 1 is 4, because we haven't considered the edge from 2 to 1 yet. So let's go back a step, and we concluded that the distance from 0 to 1 is not necessarily 4 yet, but can we say that the distance from the shortest distance from 0 to 2 is just 2? Okay, so there are people saying yes, and yes, if we assume that there are no negative, if we assume there are no edges with negative weights, the reason is that if we go to 2 with this edge 2, it has a distance 2, and if there are no negative weighted edges, then any path that we go around 2 will have a higher distance, and we can conclude that the distance from 0 to 2 is just 2. And then we can, so I think before we build our first solution, we need to observe one principle of optimality. This is called the Bellman's principle of optimality, and we will use this to build up our solution. So consider a shortest path from node S as denoted as the starting node, and T as the goal node. And let's say there's some shortest path which starts from S and passes through some middle node U, and then it might passes through other nodes, and now we land at node V, and eventually we stop at node T, and let such path be the shortest path or the optimal path. And in this case, they are just straight lines. So from S to T, there are some middle nodes U and V, and these straight lines denote is the optimal path or the shortest path from S to T. So the principle of optimality is that any subpath of such an optimal path is also optimal. So for such for such an optimal path from S to T, we can conclude that the path this path in the straight line from S to U is the shortest path from S to U, and this straight line from U to V is also the shortest path from U to V, and this straight line from V to T is also the shortest path from V to T. And the way to prove this is that actually very simple by contradiction. So if we assume there is some shorter path from U to V denoted by this curved arrow. So if this curved arrow is shorter than this straight arrow, then we will have a shorter path from S to T by going through the same path from S to U, and then through this curved path from U to V and from V to T. And this path will have a shorter distance than our optimal path, which is a contradiction. So we know that any subpath of an optimal path is also optimal. And from this, we can derive a corollary, which is that if we consider a shortest path from S to T, and we denote the node right before T as U, then we will have that the shortest distance from S to T is equal to the shortest distance from S to U plus the weight from U to T. So this is by assuming that we already have an optimal path from S to U and then to T, and we will have this relationship between the shortest distance from of the whole path, which is equal to the shortest distance from the initial node S through U plus the weight of the last edge from U to T. Is there any question? Okay, so our first solution is to try to relax edges, and we will build a naive solution. Let's assume that we will use this G variable as an estimate of the shortest distance D from S to U. So for each node U, we will have G of U as an estimate of D, and we will try to improve. We will start with G from some upper bound, for example, infinity, and then we will try to improve this G a little by a little, and then eventually this G will become the shortest distance D. The way we prove it is called an edge relaxation step. So given an edge from node U to V, we check whether given an edge from U to V, we have its G values, GU and GV, and we want to check if the path from S to V can be improved by going from S to U first, plus the weight from U to V. So in pseudocode, if we want to relax an edge between U and V, we basically check on the left-hand side, we have G of V, and then on the right-hand side, we have G of U plus the weight from U to V. So if the right-hand side is smaller, then we will improve the G values of V. And this is what we call an edge relaxation. And we can also have another variable prev, so which indicates that the previous node of V is U. So if we can find a better path, from the initial node to U first, and then from U to V, then we will denote the previous node of V as U. So with this edge relaxation function, we can already build a naive solution to find the shortest path on a graph. So given a graph of nodes V, edges E, and weights W, and also a given start node, we can find the shortest path from the start node to every single node on this path on this graph. The way that we do it is that we initialize our estimate G as some upper bound, for example, infinity here. We initialize the prev list, the previous node list, as null for now. And since we are starting from node S, we can immediately say that G of S is just 0 because the distance from the start node to itself is 0. And in each iteration, we'll try to relax all the edges in this graph. So we will call our previous function, we'll call our previous function relax on a specific edge on all the edges in this graph. And as long as there is one, as long as there is one G value that can be improved, we will continue this step. So this is a naive solution to just use the edge relaxation step, but it might have a high complexity. And our next step is to try to find some pattern that we can improve this edge relaxation step by figuring out the order that we process each node. Is there any questions for now? Okay, so let's see how we can get something better than our naive solution. Say we start from the initial node 0, and I will use the red color as the node that we are currently processing. So this node 0 that we're currently processing will have this red color, and on the right we have a column of the node and its associated G value. So we start with G of the initial node as 0. And we try to relax all the edges outgoing from node 0. So there are two edges from node 0. One is to node 1 with weight 4, and the other one is the edge from 0 to 2 with weight 2. And as you can probably remember that when we do the edge relaxation step, we check the G values of node 1 and node 2 if they can be improved by the path from here. It's from here the G at 0 plus the weight of the edge from 0 to 1 or to 2. So G of 1 will have, G of 1 will be equal to G of 0 plus 4, the weight on this edge, and G of 2 will have G of 0, which is 0 plus 2, which equals to 2. Okay, so once we have processed the edge relaxation, we need to decide what is the next node that we are going to process. And here I choose to process node 2 first instead of node 1 because of what we discussed earlier, that there might be some other edges between 1 and 2, or there are some path behind 1 and 2 that we just don't know yet. But we know for now that node 2 has obtained its correct shortest distance with its G value, because its G values, G of 2 is smaller than G of 1, which means that there are no other way around it that could decrease the G value at node 2. So we will go ahead and process node 2 here, and I'll denote the node 0 with blue color, which means that it has been processed. And again, I use red color for the node that I'm currently processing. So now we are at node 2, and we'll relax the edges on node 2. It has actually 3 edges. The first one goes back to node 0. The second one goes to node 1, and then the third one goes to node 4. We will not update the g-value at node 0 because it's marked in blue, and its distance, it's already been processed, and its distance is its g-value is already equal to its shortest distance. So we don't need to consider relaxing this edge already, but we'll consider relaxing the other two edges. So for the edge between 2 and 1, we can update the g-value at 1, which is equal to the g-value at 2 plus the weight of the edge. So this will be equal to 3. And then for the g-value at 4, that'll be the g of 2 plus 3, which is equal to 5. So once we've processed node 2, we're left with, sorry, maybe go back. So once we've processed node 2, we need to decide what is the next node to be processed. There are two options. One is node 1 and the other one is node 4. And if we look at the g values of these two nodes, from what we've seen earlier, we should decide that we need to process node 1 because it has a lower g value, which means there's no other way around node 1 that could incur a shorter distance. But still, there's some possibility to improve g of node 4 because it has a higher g value than node 1. Okay, so now we're at node 1. The nodes that we've processed in blue are node 0 and 2. And we will relax the edges from node 1 to node 3 and node 1 to node 5. So let's look at node 3. It's equal to the g value at 1, which is 3, plus the weight on the edge, which is 1, and this will be equal to 4. And for node 5, it is equal to 3 plus 10, which is equal to 13. So starting from this simple example, we can already find the main idea of what's called the Dijkstra algorithm here. So we will keep two sets of nodes. One's called closed, which means that the nodes in this closed sets are already set correctly. So these nodes are the nodes with blue or red color, where we know that its g value is already equal to its shortest distance. And we'll keep another set called open, where the nodes in this open set will have g values that overestimates the correct distance. So in our example here, the open list will be the nodes in this white color. So nodes 3, 5, and 4. So for these nodes, there is still some possibility that the g values can be improved. And initially, we only know the start nodes, so we can only assign g of s equal to 0, and we will add this into the open node. In each iteration, we will take the node from the open list with the minimum g value. The reason why we take the node with minimum g value is that we know that for this node, there is no other way around it to improve its g value anymore. And we will add this node into the closed list and relax all its edges. And then we will terminate when we find, we will terminate as long as we've found the goal node, or if the goal node is enclosed, which means its g value is equal to its actual shortest distance d. And in pseudocode, this is what the Dijkstra algorithm is. So we initialize the open list with the start node, and then the close node as an empty list. We initialize the g value, our estimates of the shortest distance, to be infinity, except for the start node, which is 0. Then we initialize the previous node list as null. And in each iteration, as long as we haven't found the terminal or the goal node T, we will remove the node U with the smallest G value from open. So for this node, we know that its G value cannot be improved anymore. We will add it to the closed list, and we will, from line 7 to 11, or to line 7, from line 7 to 12, we will relax all the edges from node U. So if there's an edge from U to V, and the G value at V can be improved by combining the G value at U plus the weight from U to V, then we will update this and add node V back to the open list. All right, so if you guys can have the repository downloaded, you can try to, if you go into the motion planning folder and scripts folder, and you can type in the command in a terminal with Python Dijkstra, and you'll be able to see this demonstration. So if we continue to our previous example, we are currently at node 1. We've processed node 3 and 5. The next node to be processed is 3 because it has the smallest G value, and we will update G of 5, which is 6. Previously it was 13, but now we have found that G of 5 can be improved by going through 3 first, and then from node 3 to 5. The next node to be processed is 4, and we will update the G value at 5 and 6. So G of 5 is already shorter, so there's nothing to be updated, but G of node 6 is a newly founded node, so it has a G value of 15. The next one is node 5. We update its, we relax its edges and update node 6. And eventually we've arrived at node 6. So now, if we look at the table on the right, we have found the shortest distance from 0 to all other nodes here, actually. So we know that the shortest distance from 0 to 6 is 10, and the path that achieves 10 is from 0 to 2, 2 to 1, 1 to 3, 3 to 5, and 5 to 6. Is there any questions here? Okay, so after this simple example on a graph, we can look at something more related to robots. So if you were here last week for our previous workshop, you might have seen this grid map. So just to pause the video here for a bit. So we're considering a grid map environments, and we discretize the space into this little squares of grid cells. So the start is this purple cell on the left, and the goal is the purple cell on the right. And I'm using the same color index as before. So for the blue nodes, those are the ones in the closed. And then for the red node, that's the node that we're currently processing. And then the green nodes are the one in the open list, for which there's still some possibility to improve their G values. And you can run this demo with this command, Python a star with this argument EPS equal to 0. So we will see that our node to be processed here is always like symmetrical around the start node, because we always remove the node with minimum G value from the open list. So our search will expand radially outwards from the start. And in the middle, there's this black wall. And for this black wall, the agent is not able to pass through, so it has to find a way around it. And eventually, it almost expands all the cells in this grid, and it finds this path from the start to the goal. So this is the shortest path from the start to goal. I think my output from that command is different. I'm not sure if you have EPS. If you also put in EPS equal to 0, then it should show this. Yeah. Okay. Maybe there's some bug in the code, and yeah, maybe we can try to figure that out later. Okay. So our next step is to try to improve this Dijkstra algorithm a little bit, as we've seen in our previous demo, that when we try to find a path from the start to goal, it almost searches through all the possible nodes in this grid. So is there any way to improve the Dijkstra algorithm? So we observe that in each iteration, we pop the node from open list with the minimum G value. And this G value only contains the information from for the distance between starts to the current node U, but it does not provide any information of where the goal is. And ideally, we want to lean our search towards nodes that are closer to the goal. The way we do this, or the way we as designers can provide this extra information, is through a heuristic function. So a heuristic function is just some estimates that we provide to the algorithm as the distance between the current node and the goal. The goal of this heuristic function, yeah, thank you for figuring. So there might be some bug in the code, and thank you for figuring that out. Okay, so the goal of this heuristic function is to reduce the number of iterations in the Dijkstra algorithm. And depending on what kind of heuristic function we provide, this search can be faster or slower. So the more accurate heuristic that we provide as the distance from the current node to the goal, the more efficient the search will be. And if we consider examples in this grid world, then we can have 2 or maybe more types of heuristic functions. The first one is the Manhattan distance. So for 2 points, X and Y, the Manhattan distance is the sum of absolute values in each dimension. And there's also the Euclidean distance, where this distance is just the length of that line between X and Y. So on a 2D plane, a Manhattan distance equal to 1 will look like a a square or a diamond shape, whereas the Euclidean distance of 1 would look like a circle. Okay, so just by providing this extra step of information into our previous Dijkstra algorithm, we can get an improved algorithm, which is called A star. So the only thing that we changed here is that when we try to remove a node from the open list, we not only look at its G value, but also an additional term, epsilon times the heuristic between the node U and the goal T. So this epsilon is a multiplier that we can set. So if epsilon is a large positive number, then we will weigh the importance from U to T more than the distance from S to U. And if we set epsilon to 0, this term is just G of U, and it is we can get back our Dijkstra algorithm. Okay, so again, back to our grid example. Here I'm comparing the A star algorithm with 2 epsilon values. So you can type in epsilon equal to 1 or epsilon equal to 5. And on the left, it's epsilon equal to 1. We've seen that there is some improvement over the Dijkstra algorithm. So it doesn't, previously in Dijkstra, we've expanded all the nodes here in the corner. But since we know that the goal is on the right, we actually don't need to look for these nodes because they are already far away from the goal. And with epsilon equal to 1, this is the region that we've searched in our closed plus open list. And then with higher epsilon, with epsilon equal to 5, we can even reduce the number of searches. And you can see here that it has a smaller region. So you can play around with this epsilon, and hopefully maybe there's some bug in it, but I'll try to fix it later. And you can see the different effects of this epsilon value. So epsilon equal to 0 is just the Dijkstra. Epsilon equal to 1 would weigh the distance from start to current node equally with the distance from the current node to the goal. So there's a question, is it common to use epsilon or use a weighted average of G and heuristic? Yeah, so basically this epsilon is just a way to provide a weighted average between G and H, the heuristic. And it's just that this weighted average is determined by us. We can determine how fast we search for the goal. And the larger the epsilon, the faster we get to the goal. But there are some additional things we need to pay attention maybe, but probably beyond the scope of this workshop is that with larger epsilon, the path that we get might not be optimal. It might be suboptimal. So we get a faster solution with a larger epsilon, and the price we pay is that the solution is could be non-optimal. Is there any other questions? Yeah, so there are some other visualizations online that you can play with. If you can click on, yeah, so this slide again is available on the main page of the repository, and you can click on these cool visualizations. I think you can also draw your own wall, and there are different type of algorithms that you can choose from. And they all give very cool visualizations. So are there any questions for Dijkstra and A star? Yeah, so what we've seen so far is that given a graph, we can find.
So how do you, can you hear me?
Yeah.
So how do you determine the heuristic function?
So sorry, just I'm trying to paste these visualizations to our chat box so you can try out here. And then the last one. Sorry, just 1 second.
Sorry, Tianyu, do you mind if I share my screen just for a second to show the visualizations while you take the question?
Okay, yeah, so I'll take the question, how do we determine the heuristic function? So if we go back to our grid example, the heuristic function is what we designer provide to the algorithm. So if we know that this grid, so if we know the patterns of this graph, for example, as a grid, so in this grid, we're only allowed to travel to the cells that are up, down, or left and right, then we will use the Manhattan distance because that is the distance in this grid world. Or if we if we design a grid where we allow diagonal moves, so for each node, for each cell in this grid, we are allowed to go not only up, down, left, right, but also diagonally up, left, and up, right, and down, left, and down, right, then we can use the L2 norm, the Euclidean distance.
So there are standard heuristic functions like.
Yeah, there are standard heuristic functions. So there are other things to note, like the heuristic function should really underestimate the actual distance from current node to the goal. So the heuristic function should not be larger than the actual distance from the current node to the goal. It can only be equal or smaller. And in this grid world, we can know that if we only allow up, down, left, right, then the Manhattan distance will always be equal, smaller or equal to the actual distance.
Okay. And how do you determine the epsilon value? Like, is it trial and error?
Yeah, that's something you can determine yourself. It's just a trade-off between how fast you want the search. And so the larger the epsilon, the faster the search, but also the more suboptimal the solution. So if you want a correct solution, really the optimal solution, then you will set epsilon equal to 0 or equal to 1 if your heuristic is an underestimate of the correct actual distance. And if you make epsilon larger, then you'll pay the price of getting a suboptimal solution.
Got it. Thank you.
Yeah.
Yeah, I just wanted to highlight one of the links that Tianyu put in the chat. So Tianyu, if you don't mind, I'll share my screen for just a minute.
Yeah, sure, go ahead.
So I went on the first link in the chat, and this is how it looks like. You can build your own map here. So I built some symmetric thing just for fun, and then we can try to run something similar. So here on the right, you can choose the different kinds of algorithms you want to try. So far, Tianyu discussed the Dijkstra algorithm and the A star algorithm. So we can look at one more visualization here. So let's start with Dijkstra. We can allow diagonal moves, and then let's see what this will look like. So when I do start search, you see something similar to what Tianyu's visualizations were. The blue area are the open lists, are the nodes in the closed list, sorry, while the green nodes over here are the nodes in the open list. So as Tianyu mentioned, you can see that this Dijkstra algorithm doesn't have any sense of what direction is preferable and kind of expands everything until it finds the optimal path. While if we switch to a star, we can now introduce a heuristic, and here we have a choice between Manhattan, Euclidean, and then some other choices. So let's use Euclidean with diagonal movement and repeat the same search again. And we're going to see something very similar to the behavior you saw from Tianyu's algorithm earlier. So because I made the map pretty challenging, I think our heuristic is actually not very helpful in this case, but still a star expands a bit fewer checks or it computes things for fewer nodes than the extra. And then there are other algorithms, if you're curious, you can look into later on. So there's, for example, jump point search is a pretty cool algorithm. It's outside of what we're going to discuss today, but just as to compare to what we saw earlier. So here's how the jump point search algorithm will work. So it actually visits all of these blue and green nodes, and it's able to jump over these gray ones. So it actually doesn't have to consider those in its search. So it has some smarter way of breaking symmetric paths and only considers ones that will not be symmetric. So it looked like it took longer, but you can compare kind of the time that the different algorithms take here. Yeah, that's just wanted to point out this website is another cool way to visualize and understand what the different algorithms are doing. So I'll switch back to Tianyu now.
Okay. All right. So we've touched on how to solve the shortest path problem on the graph. And we look at some visualizations on the grid. And let's consider another problem that's kind of more realistic in a robotics setting. So let's consider that our robot is now at this green spot. And before we start to process the search, we actually don't know what the environment is. So in the previous case in the grid, we've already known where are the walls, where are the free cells, so for each step in that search, we know like what is the next cell that I can go to. But now let's imagine we are in a environment where we don't know the where the obstacles are yet, and we have some sensor on our robot that is able to detect these obstacles. So let's say we have a LiDAR sensor that's from this green cell that it shoots like straight lines towards each angle in 360 degrees in this plane. And so if we were here last week, we've also talked about LiDAR sensors. So once it hits an obstacle, it will return the distance to that obstacle, and we are able to mark these cells as black if they're obstacles. And if it doesn't hit anything, we'll mark the cells as white, which means these areas are free. And for the gray ones, we still don't know whether it's an obstacle or a free cell. So what we have here is that we know the start, we know where the goal is in this purple dot in this environment, but we don't know the exact locations of all these obstacles. On the other hand, we have a LiDAR sensor that is able to detect where these obstacles are around the robot. And to again, our question will be, what is the shortest path from our current state or the start node to the goal? Yeah, so an additional constraint is that our robot cannot hit an obstacle. So how can we try to find a path from our current state to the goal without knowing what potentially what obstacles are there in the environment. We definitely need to move around to expand our explored region. So initially we start at this green dot location. If we move down a little bit, we are able to see some more area on the bottom right of this left. Bottom right of this white region. And on the left, we can also expand some more region around here. And as we move further, we're able to expand even more. And maybe let's go down. It's in this figure, if we go down this corridor a little bit, we can find out the more free spaces down here. So our task will be to observe what obstacles are there in this environment, and then plan some trajectory that will take us to the goal. So how can we set where we want to go? Can we set just some random point as a goal, or can we just run our Dijkstra or A* algorithm with this purple dot as the goal? So the answer is probably not, because we don't know what is the map like in this gray area. Is there any obstacles? Is it just free regions that we can move without hitting any obstacle? So what we'll do instead is that we will plan some trajectory that is guaranteed not to hit anything. And at the same time, we will expand our observed region. And eventually, as we expand this, observed region more and more, we will hopefully we'll find where the goal is, and we will traverse to that goal. So the way we set this temporary goal location is by looking at the frontier of the observed region. So let's start from the initial observation from the start location. The white region is what we observe as free area. And these cells that are between or on the boundary of the white cells and the gray cells are what we called a frontier cell or a frontier node. So these are the nodes that we can guarantee that there is some path that we can traverse from our current location to this cell. The reason is that we detect in our observation, we did not detect any obstacles to this frontier. So we know that there must be some way to maneuver from our current location to this to any cell. In fact, for any cell in this frontier. And then, so let's say we set some location in the frontier as our first temporary goal. And since we already know that there must be some path that can take us from our current location to this first temporary goal, we can run our Dijkstra or A* algorithm to return that path. And we just follow that path to this first temporary goal. And along this first trajectory in the red dots, we can also receive LiDAR observations as our robot moves to a new location, and we can build up our map incrementally like this, and our frontier cells or frontier region would also change dynamically as we travel from in this red path. So now assume that we have finished this first path and we are at this green dot location. And again, we'll go back to our previous solution. we'll look at all the frontier cells and pick some frontier cell that as another temporary goal, and then travel to that temporary goal. So in order for us to reach the goal location incrementally, we will actually pick the frontier cell that is closest to the goal. And we can we can use some heuristic function like the Manhattan distance heuristic function, or the Euclidean distance heuristic. So in the second iteration, we will travel through this blue line. And now we are here. And again, we ask what is the closest front cell to the goal, and it's this purple cell. We set it as another temporary goal, call our Dijkstra or A-star algorithm. And this is our solution for planning a path in an unknown environment. So in our pseudocode, we will start with our current robot state as the start state. We will initialize an unknown grid, let's call it M. And in this case, initially, we will initialize an unknown grid, which is gray everywhere. We update the grid with our LiDAR initial LiDAR observation at the start location. So our LiDAR would return the distance to the closest obstacle, and we can build a map from the LiDAR readings and find which area is free and which area is obstacle. In our main loop, while we haven't found our goal yet, we will find the frontier of our current explored region, which is the boundary between the free cells and the unexplored region. So if there's no frontier to be found, which means that basically we have explored all the environment in this, well, we have observed all the environment, then still there's no, still we haven't seen the goal, then there's no feasible path from the start to the goal, meaning there's no path that we can travel from the start to the goal. And if there's some frontier cells, we will find among these the closest one to the goal and set it as our temporary goal. And we will call Dijkstra or A-star here to find the path from our current state, current node or current location to the temporary goal. And as we follow through each location in this path, we will update our grid with the LiDAR observation. So in our repository, if we can run our third demo, you'll see something like this. So initially, it picks some temporary goal, and it will start expanding the explored region with its LiDAR observations. And eventually, it will find where the goal is. And are there any questions from here? Okay, so go back. So there's a question on how find the closest point works. So so we're referring to this line 9. So we're trying to find the closest point within the frontier to the goal. So let's look at this example first. let's look at the left figure as an example. The green cells are the frontier cells. So this is the input to this find closest point function. And basically it's just a list of all the nodes in this green. And for each node, we can compute a heuristic from this node to the goal. So we can use the Manhattan distance heuristic or the Euclidean distance heuristic. And this will return us some estimate from of the distance from the green cells to the goal in purple. And within these cells, we will find one with the shortest distance. So in this example, this cell in probably pink or light purple has the shortest Euclidean distance from within these frontier cells to the goal.
And what if the goal location is not known? Like a goal, you know something, you have to get something, but you don't know where it is. So is that a sort of path planning problem, or is it?
Yeah, so that is, so here we only consider that the goal is known. So if we need to add in perceptions, so let's say we want to find a specific object of interest, then we would need to like add in an additional module that says like, this is the object that we need to find.
On top of path planning, or like?
Yeah, on top of path planning.
Okay. So in that case, how do you determine the heuristic, like the closest path?
Yeah, in that case, since we don't know where the goal is, then there is no heuristic. So maybe like, let's imagine I'm in a room that I've never been before, and I'm asked to find, let's say a cup, a specific kind of cup. Then my only like one solution would be just walk around the room and just try to find if I've found the cup or not. And really, there's no heuristic on where the cup could be if I don't know any information about the room.
Okay, thank you.
Yeah. You will use DFS, depth first search, instead of priority queue in that case, right? So I think, so there are other possible ways to find a path. So for example, depth first search or breadth first search. They can also, they're similar to Dijkstra, and you start from some initial node, you don't need a heuristic, and you just keep expanding or relax the edges. And in that case, yes, you can use either Dijkstra or DFS or BFS if you don't want to consider any heuristic to the goal, yes. Okay, the question is the next temporary goal only chosen after reaching the current temporary goal? Yes, so in each iteration, we only consider its current temporary goal. We call A star or Dijkstra to find the path to that goal and accumulate all the observations along the path. Once we've reached that temporary goal, then we will consider what is the next temporary goal. And I wonder if it's possible to even desirable to update the temporal. Yeah, so here, since this is a simple scenario, we don't consider any noise in our observation, then we know there's really nothing to lose if we just go from the current state to our current temporary goal. But if there's some noise in the observation or some noise in the mapping, then we probably need to do replanning at each step. So as we get more and more information at each step, we could update our previous path search solution. Sorry. Are there any more questions? Is there any trouble running the demo in the repository? Okay, if that's it, I'm pretty much done with what I want to present here. And thank you everyone for listening. Nikolay, do you have anything to add?
Thank you, Tianyu. No, I was just going to say we're going to make the slides, and the slides are already there, and the recording as well later on in case you want to check our discussion again. Both will be on the website, and we're going to keep this website open if you want to check out the code later on. If you have suggestions for improvement, feel free to. So if you open the GitHub page on the top, Tianyu, do you mind showing the GitHub page and where you can submit an issue if you have any suggestions for improvement or you find any problems? That's one way to let us know. Yeah, and I guess next week we'll continue with optimization. I don't have anything else particular. I think Tim or Belinda, if you guys have anything else you wanted to add.
Thank you so much for attending the event, and then also for presenting, Tianyu.
Oops, I accidentally turned off my video instead of unmuting. Yeah, thank you guys so much for presenting the material. I hope everyone learned a lot from today's event. We'll have another one next week. If you have any questions, feel free to stick around because we are ending early. And as for HCAN inductees, make sure you check off in the Discord channel. All right. Does anyone else have any questions? Feel free. Justin, is that a question directed for UCSD or SDSU, by the way? UCSD. So it kind of depends on what you're looking for. You know, obviously HCAN is great. I think to get involved, there's also a lot of other organizations. I think, yeah, tabling just finished for UCSD's ECE day today, but Project in a Box does like project-based stuff. IEEE, I think at both branches, SDSU and UCSD are fantastic. We also ACN focuses more on the software side of things, as well as ECUSC, Undergraduate Student Council, to get involved technically and like socially.